Hi everyone, my name is Duong and I am an undergrad student in Institute and Technology. And today I'm going to present the topic called Circumscribed Circles and Polygons. Let me introduce you the problem. So if I have a first circle and draw outside circumscribed by the triangle and another circle and keep going with the polygons, which is a square, and the next one is a circle and a pentagon later. The question is, will the figure below become arbitrarily large or remain within the bounded region? So what do you think? Is it gonna become infinite number of the radius for the circle, or will converge at some point? Let me prove it to you. So let's take a look at the radius. So I'm gonna call the first radius R1, which is the length right here, as 1, assume it's 1. And I can compute the R2 by using the cosine, the angle, this one right here. So R2 will equal to R1 over cosine of the angle 3. I will call this angle 3 because the triangle right here has 3 sides, would make it easier. Continuously, I do the same thing for the next R, which is R3 right here. R3 will equal to R2 divided by cosine of angle 4. So on for the larger radius. Now I'm going to use a substitution, as we know that R1 is equal to 1, R2 equal to R1 multiplied by secant of the angle 3. R2 will equal to 1 multiplied with the secant angle 3 as well. So I'm going to use substitution by R3 will equal to R2 multiplied with secant of angle 4 and so on. Therefore, as you put it together, it will be R4 will equal to R1, and then 1 multiplied with secant angle 3 multiply secant angle 4 multiply secant of angle 5 and infinity. So we can write it as a product of the secant angle n, starting from n equal to 3 to infinity. So how do you estimate the radius of the product secant of the multiple angle starting from n equal to 3? We're going to start with 1 unit radius circle and then inscribe by the equilateral triangle. So the angle 3 right here, which is the 60 degree, that means it's pi over 3, since R2 is the angle bisector of the one angle of the regular triangle. And the next one, which is the angle 4, all equal to 45 degree, which is pi over 4. Same thing for angle 5. It's going to be pi over 5. So angle n will equal to pi over n. We can use the product of secant pi over n to plug the number in and see what we're gonna get. So I'm gonna take the natural log of both sides. The reason is I want to change it from the product to the summation, which will make it easier to work with. So I'm going to take the natural log on both sides. It will give me a natural log of secant pi over 3 multiplied with secant pi over 4. You're going to use the property of the natural log, which is become a natural log of secant pi over 4 plus natural log of natural log secant pi over 3 plus natural log secant pi over 4 and so on. It will give me the summation of the natural log secant pi over n. I usually change whatever secant or cosecant to sine or cosine, so I would write the summation as the negative summation natural log cosine of pi over n. Therefore, we will know that the natural log of r will equal to the negative summation natural log cosine of pi over n. So how do you compute the cosine pi over n? Right here, I'm going to use the Taylor series to compute cosine pi over n, which is 1 minus pi over n squared over 2 factorial plus pi over n to the 4th over 4 factorial. So when n becoming really large, we can estimate the cosine pi over n equal to 1 minus pi over n squared over 2 factorial, which will become 1 minus pi squared over 2n squared. So we can conclude that the negative natural log cosine of pi over n is approximately equal to negative natural log of 1 minus pi squared over 2n squared when n is really large. The same method, we're gonna estimate this one by using a Taylor series. So natural log of 1 minus pi squared over 2n squared will equal to negative pi squared over 2n squared minus pi to the 4th over 4n to the 4th. The same thing if n become really large, we can estimate this natural log equal to negative pi squared over 2n squared by using a Taylor series. So the natural log of r equal to that summation negative natural log of cosine pi over n will converge or diverge. We're going to use the limit comparison test for the summation of pi squared over 2n squared and with the summation of negative natural log cosine of pi over n. We're going to take the limit of this summation of this one over pi squared over 2n squared by using a L'Hopital rule. We're going to take the derivative of the top one over the derivative of the bottom one until we can conclude until the top one equal to the constant over cosine square of pi over n will approximately 1. So both series are converge or diverge. The next one, we're gonna prove that this is converge or diverge by using a p-series of the series of 1 over n to the power of p will convergent. This is recall of the p-series test. Convergent if p is larger than 1 and divergent if p is less than or equal to 1. So since the summation of pi squared over 2n squared equal to pi squared over 2, the series of 1 over n squared is convergent. Therefore, the summation of negative natural log cosine pi over n is convergent. So I use the MATLAB to calculate the radius when n is equal to 1000. The radius is approximately 8.657, and until 10 million, the radius is 8.700032, and then until 1 trillion, the radius is just a little bit of larger than the 10 million one, which is 8.700037. And I make the video of how the polygons and the circumscribed disorder. And this video I make by the MATLAB code and convert into API. You see the circle right here, the red circle outside, actually the radius of 9. But when this one, as it's going, it's approaching that one, but it's never touched the red circle outside. This is the original problem that I found from the book. But back in the day, their approximation is wrong. The increasing radius across the limit approximately 12 times that original circles, which is not what we come up with. Maybe in the future, if we have quantum computer, we probably can compute the radius.
Okay, thank you.
Thank you.